Good afternoon. Let me share my file. Okay, we continue the moment and impulse equation with some examples. Here we have the center O of the wheel has a velocity of 2 meters per second. V1, this is the first or initial velocity for the wheel, which is in upward direction. And the 10% incline at time t is equal to 0. So this is the initial velocity. Find the velocity v2 of the wheel when t is equal to 6 seconds. The wheel has a radius of gyration of 90 millimeter and rolls without slipping. So we can write and solve this problem using the Newton's second law. If we want to use the Newton's second law, we need to write the force equation in the x direction. For example, if we assume this is the x direction, we can write the force equation in x direction. We can obtain the acceleration according to the direction of the motion and the direction of the weight. The acceleration will be negative in this case. When the acceleration is negative, it means v1 will be decreased, and after the while this wheel will be stopped and then start to move to the downward direction, and we should calculate the acceleration during this motion. It will be a complicated procedure to obtain the velocity using the Newton's second law. I mean, you should find one acceleration during the motion in upward direction. Again, you need to find the acceleration in downward direction. You should find exactly at which position the wheel will be stopped and start to motion in downward direction. And you will have a lot of complicated calculations. But if you use the impulse and momentum equation, you will see the procedure is very simple, and the calculation is significantly less than the Newton's second law method. So we solve this example using the impulse and momentum equation. We can write the moment equation about point C. As I told you, here we have the rotation without the slipping. And as I mentioned several times, when we have a rotation without the slipping, it means that we can assume this is a fixed point. This point C, in fact, is a fixed point. So point C can be considered as a pin connection. Here we will have a pin connection. So you can write the moment equation, the momentum and the impulse equation about this point C. So we can write the moment about C, it's equal to h dot C, or the rate of change of angular momentum about point C. In the integrated form, we will have this equation, hc1, the initial angular momentum about point C, plus the impulse during t1 to t2, which t1 is equal to 0 and t2 is equal to 6 seconds, we know, is equal to the final angular momentum about point C. So the summation of the moment about point C is equal to IC omega 2 minus omega 1. If we calculate this integral, we will have the summation of the moment about point C times by t, which this t, as I told you, is t2 minus t1, which in this case is equal to 6 seconds, is equal to IC omega 2 minus omega 1, because hc1, or the initial angular velocity, angular momentum, sorry, is equal to IC times by omega 1, and hc2, or the final angular momentum, is equal to IC times by omega 2, which is the final velocity. So we can find this term, but we need to calculate the summation of the moment about point C. If we plot the free body diagram for this wheel, we can find that the moment about point C is equal to only the weight will create some moment, because we have one weight here, which this weight, or mg, this vector has two components, one in perpendicular direction to the inclined surface, and the other one which is the parallel to the inclined surface. Also, we have two forces here. One is the normal reaction, the other one is the friction force. These two forces, because both of them located on point C, they don't have any moment. There is no moment due to these two forces. Only the horizontal component of this weight, of course, I mean by horizontal means that parallel to the inclined surface. So the parallel component of W or mg will create a moment, and it's equal to mg sine theta, and the moment is equal to mg sine theta times by the arm, which is this length. The arm is this radius, is r. So this is the moment about point C. And I see the mass moment of inertia about point C is equal to the mass moment of inertia about the mass center, which is mk squared. This is k is the radius of gyration, plus md squared, which in this case, d is equal to r, the radius of the wheel. So finally, we can calculate IC, the summation of the moment about point C, and also we have T. Omega 1 and omega 2, because the motion is rotation without slipping, and there is no slipping during this motion. So omega 1 and omega 2 are equal to the linear velocity divided by the radius. Or we can write that V1 is equal to omega 1 times by r omega. So omega 1, the initial angular velocity, is the initial linear velocity divided by radius. Okay. So this is omega 1, and omega 2, or the final angular velocity, is the final linear velocity divided by radius again. So we can substitute these terms and simplify. And finally, we can find a relation between V2 and V1. Here, we can substitute the numerical values. R is the radius of this wheel, which the diameter is 300 millimeter. So the radius is 300 divided by 2, or 150, which is equal to 0.15 meters. Sine theta, which theta is, here we have a 10% incline. So theta is clear, theta is tangent inverse of 1 divided by 10. T is equal to 6 seconds, because we want to obtain the velocity after 6 seconds. K is the radius of gyration, and R again is 0.15, and V1, which is the initial velocity. Here we assume that the direction in downward direction is positive, so V1 is negative. Okay. So this is the total procedure to obtain the velocity of this wheel after 6 seconds. Okay, any question? Okay. Okay, next example, we have uh, an impact. In fact, the 1 divided by 16-pound bullet has a horizontal velocity of 1,600 foot per second as it strikes the 55-pound compound pendulum, which has a radius of gyration 37 inch. If the distance h is equal to 43 inch, calculate the angular velocity omega of the pendulum with its embedded bullet immediately after the impact. So here we have first a compound pendulum, which is initially at rest. We have one bullet. The bullet has a weight of 1 divided by 16 pounds. It will strike the pendulum in the position of H, which this H is equal to 43 inch. The position of the mass center for this pendulum is 35 inch lower than point O. We want to calculate the angular velocity of this pendulum after the impact. So in this type of problems, when we have impact, as I told you, the best option similar to the particles is using the impulse momentum equation. So we can write the angular momentum impulse equation, of course, in integrated form. We will have the initial angular momentum about point O plus the impulse about point O, it's equal to the final angular momentum about point O. Since there is no external force and there is no moment about this point O, only we have the weight. If we consider here, we have this weight, the weight passing through point O. So there is no moment due to this weight or due to this vector about point O. So this term is equal to 0. The moment about point O is equal to 0. And we can conclude that the initial angular momentum is equal to the final angular momentum. So this is the impulse momentum equation. So the initial angular momentum is equal to mvh because this pendulum is initially at rest, so there is no angular momentum for this term because omega is 0 or the velocity is 0. But this bullet with mass 1 divided by 16, it has a momentum about point O, and the moment of a particle, in fact, we assume that this bullet is a particle. The moment angular momentum due to this particle about point O is equal to mvh, which v is the velocity, m is the mass, and h is the distance between this particle and point O. Or as I told you, it's like the arm when you are calculating the moment, which for this velocity direction is h. So m is 1 divided by 16. This is in pound. We should convert it into the slug or the mass pound. So we divided this by 32.2. V, the velocity is 1,600 foot per second, and h is 43 inch. We should divide it by 12 to convert it into foot. So this is the HO1. For HO2, or the final angular momentum, we have a pendulum which start to rotate about this point O. And also we have this bullet which is stick to this compound pendulum, and it's rotating both of them at the same mass. So the angular velocity for both masses is the same, and both of them we rotate with the same angular velocity, which we assume that that's omega. So we can write the angular momentum after the impact in two different portions. The first part, this part, is the angular momentum due to the pendulum, and this term, which is the angular momentum due to the bullet. So this term mhv is the angular momentum due to the motion of the bullet. So we will have ig omega mv bar d. This is in fact the angular momentum of a rigid body about any other point which is rotating, a fixed point of rotation. So we can write Ig omega plus mv bar d, which Ig is the mass moment of inertia about the mass center. Omega is the angular velocity. V bar is the velocity of the mass center. And d, which is the distance between the mass center and point O. So we can substitute into this equation to find the angular momentum of the compound pendulum. And mhv is the mass of the bullet times by h, which is the distance between the bullet and point O. And v is the velocity of the bullet after the impact. And we know that the bullet will rotate about point O with the same angular velocity omega with this compound pendulum. So we can find that V is equal to H times by omega. So here it will be mh squared times by omega. So we can substitute and find the final angular momentum as this term as a coefficient of omega. So HO1 and HO2 must be equal. So we can substitute and find that omega is equal to 0.3613. So this is the final angular velocity. Okay. A uniform standard bar of mass m and length L is translating on the smooth horizontal xy plane with a velocity Vm when a particle of mass m traveling with a velocity of Vm as shown asterisk then becomes embedded in the bar. Determine the final linear and angular velocities of the bar with its embedded particle. So here we have one cylinder with uppercase mass m. This mass, it's moving with a horizontal velocity v sub uppercase m. Also, we have a particle with lowercase mass, lowercase m, and the velocity of v sub lowercase m in vertical direction. So this particle restricts and become embedded in the bar, and we want to obtain the angular and linear velocities of the bar after the impact. So the linear velocity can be easily obtained from the conservation of linear momentum, but for the angular momentum, we can use the angular momentum impulse equation. So we consider that after the impact, the position of the mass center for the compound system includes the particle with mass m and the cylinder bar is at point G2, and xg, which is the position of G2 with respect to the point of the impact. So we can write the linear momentum equation in x direction. It's equal in x direction before the impact. The initial linear momentum is the mass of the bar times by its velocity. And after the impact, we will have the mass of the bar plus mass of the particle times by Vx, which Vx is the velocity of point G2 after the impact. So Vx is equal to mvm divided by m plus m. So this is the velocity of the mass center in x direction after the impact. And if you write the same equation in y direction, this time before the impact, The particle has the velocity of Vm, of course, V sub lowercase m, times by the mass of the particle. After the impact, the mass is m plus m, the mass of particle plus the mass of the bar, times by Vy, which Vy is the velocity of the mass center G2 after the impact in vertical direction. So Vy can easily obtain from this equation. The next step, we need to calculate the xg, or the position of G2, or the mass center after the impact, when these two particles convert into one mass. So here we can write about an excess passing through this point. If you write and calculate the mass, or the mass center for this compound system, we will have xg, the distance between two G2, which is the new mass center, times by xg, and the mass is for G2 is m plus m. It must be equal to the mass of the bar, which is G1 here, times by its arm, which is L divided by 4, and it's this length, L divided by 4. So xg can be calculated from this equation easily. And now we can write the angular momentum in about point G2, or about the mass center, the new mass center. Before the impact, the angular momentum about point G2 is equal to the mass of the particle times by its velocity times by xg. But the mass of the slender rod, because this impact exactly parallel to um, horizontal direction, and it's the velocity vector passing through the point G2, so it doesn't have any angular momentum about G2. But after the impact, we will have one angular velocity for the bar, so it will be the Ig2 times by omega. And also we have the velocity in y direction for the particle after the impact, times by its mass times by the r, which is xg. So we can calculate Ig2, which is the mass moment of inertia about point G2, and it's equal to the mass moment of inertia about the first mass center, plus md squared, which d is equal to L divided by 4 divided minus xg. So we can substitute here. And also we know that the velocity of particle after the impact is equal to xg times by omega, because in fact this, we can assume that this particle, this bar is rotating about point G2. So the velocity of this particle, which is located in the distance of xg, is equal to xg times by omega. So we can substitute into this equation. We have Vm, we have xg, which is calculated here, and we can substitute and simplify, and finally we can find that omega, the angular velocity after the impact for this bar, is equal to this term, which is a function of Ig2, xg, and Vm. Okay. If you don't have any question, we can have a 5 minutes break, and after that I will start again and continue.